Hi, so today I'll be explaining about this question. For this question, I already map out all the info that is given to us, and this question wants us to find the mass flow rate. So first of all, we need to assume. So what we can assume is actually it is a steady flow, because like there's nothing like the volume that is coming in is actually equal to the volume that is coming out. And because there's no info about kinetic energy, about potential energy, about work, and about heat loss from the device to the surroundings, then we can assume that it's actually equals to zero, and we neglect these things in the energy balance equation later on. And the air here, we will assume that it's actually like ideal gas, so we can use the ideal gas constant of air, and then we can know that we can use the constant pressure specific heat of air, which is equals to 1.005 later on. So first of all, with this information, we need to know, we can extract that the H of the refrigerant is actually H1 is equals to 324.66 kilojoule per kilogram, and for H2 is actually equals to the HF, which is equals to 93.58 kilojoule per kilogram. Okay, now that we have all this information, we can actually know what is the specific volume at the inlet. Okay, using the ideal gas equation. So V at 3, V3 is equals to RTP1. Okay, and we just substitute the information. To get 300 Kelvin, we just substitute from 27. We just convert the unit to Kelvin from degree Celsius, and then 100 kilopascal. Yes, thus we will get 0.861 meter cube per kilogram. And because we already got the volume of it, so we can actually find the mass flow rate. Mass flow rate for air. Then we will get 696.9 kilogram per minute. Okay, now we can actually know that this whole entire system is actually an heat exchanger, and it's a control volume, because like the volume is steady a long time. Now we can actually write that actually the mass balance for each of the fluid stream is like mass flow rate in is equals to mass flow rate out. Why? Because mass flow rate in minus mass flow rate out is equals to mass flow rate of the system. And then because it's actually 0, then mass flow rate in is equals to mass flow rate out, and from here, we can know that mass flow rate at 1 is equals to mass flow rate at 2, which is mass flow rate of refrigerant, and mass flow rate at 3 goes to mass flow rate at 4 to mass flow rate of air, because it doesn't change. Okay, and now we can write the energy balance. We know that the formula for energy balance is E in minus E out equals to E dot system, and E in equals to E dot out because it's actually equals to 0. Now what do we have here? We can write the Q dot in goes to plus okay. So because like we already say that we got the assumption already, so we can cancel out the things that is not needed. The Q is 0, the work is 0, the kinetic energy is 0, and then the potential energy is also 0. So we can just cancel it out, and we are left with delta M H equals to delta M. But then actually we know that the M there is actually it's from the wait, we can just write first like this, right? But then it's actually in and out. So we can write what it is that comes in. So what comes in is actually what comes in m dot 1 plus m dot 3. But then we know that the one at 1 and 2 is actually R, and the one at 3 and 4 is actually air. So we can just write 1, 2 is R, and this one is air. Okay, so we can simplify it better now. We can see that m dot A H1, m dot R H3 minus H4. Yes, now we can actually solve for m dot R because that is what they are asking of us. Let's simplify first. H2 minus H1. Okay, so from here, actually we can simplify this equation here. We can write it as specific heat T2 minus T1 H3 minus H4 mass flow rate of air Okay, now we just substitute. That's the specific heat. 60 minus 37 is the temperature in degrees Celsius, and the H3 is 324.66 minus H493.58 times the mass flow rate of air, 696.9. Thus, we get the final answer like this.